Mr. Stephen, we have to stand here, everyone, to pick that up. It's a little bit, I know. Okay.
My name is Dr. Stephen Jones, and I'm Associate Dean here in the College of Engineering, Villanova University. We're so happy that all of the parents and friends and family have come to celebrate what the students have done over these last 2.5 weeks. Let's give them a hand. This took a lot of hard work and late nights to get this all together. And Dr. Hampton, does you want to share words of welcome as well?
Yes, I'd like to welcome all the family members who could be here, and thank you for sharing your students, or your children, our students really, for the past 2.5 weeks. We've had a really great time with them. And I'd like to also thank, we have a couple representatives from the LEAD organization in the back. So we'd like to thank you. You can stand up. We also collaborate with Dow Chemical. They're one of our main sponsors for our program. And we have one of their representatives, Ms. Eunice Heath, with us today. She's a global director of worldwide sustainability for Dow. And I'd also like to have any faculty advisors, graduate student advisors who are here to stand up so we can thank you for your hard work that you contributed to the program. Okay, so without any further ado, I think that is all I have to say. We will start with the electrical. I'm actually not going to say that. I'm sorry. I'm taking somebody's thunder away from them right now. So our moderator, I want to say MC, but it's a professional presentation. So the session moderator for this morning is our head RA, Miss Brittany Wyatt.
Good morning, everyone. To start off, we will have the Electrical Engineering Renewable Energy Group.
Good morning, everyone. My name is Adriana Pagan.
I'm Harrison Getter.
I'm John Benesai.
I'm Viviana Santiago.
I'm Morgan Reed, and we're the Electrical Engineering Group.
So during this project, we learned about renewable energy and how to power a rural house in Nicaragua. So our problem statement is, how can we use renewable energy to power a rural house in Nicaragua? So quick solutions. Because the house is so far away from the grid, it would be very expensive and not cost efficient to extend the grid to the rural parts of Nicaragua. So what we decided was to build a self-sustainable system right in the person's house. So there were many ways you can do this, but the two that we focused on were solar energy and hydroelectric energy.
So in our time with electrical engineering, we worked with our advisor, CHARACTERIZATIONS, to learn the basics of the field. So that is learning what electricity is, where it comes from, and how it's brought into our homes. After we learned the basics, then we started working on 2 separate labs on how energy can be generated with renewable sources. That was with the hydroelectric generator in the lab and also the solar panels. Then once we did those 2 labs, we were able to determine which would be the most efficient means to be used for the rural home in Nicaragua. But before we go into that, we first would like to share with you the concepts and then go over the labs and then describe to you our project. Right here is an example of a rural home in Nicaragua given to us by our head advisor, Dr. Singh. This is what you would most commonly find in this rural region. A small little shack area, far away from most cities, and with lots of trees and tropical environments.
So to start off with our explanation of the project, I would like to explain some important concepts that you should know. The first one we learned about was voltage, which is the strength of each power source in the circuit, and basically how fast, like how strong the electrons in the circuit are. So the unit for voltage is volts, and you can see right here it's represented with a V. And basically when we have a higher voltage, that means that the circuit has more electric potential. We also learn about current, which is just basically the flow of the electrons through the circuit. It is measured in amps. And we learned about two types of current, which are alternating current. This current will vary through time, and its graph is like the sine graph, so it'll have a constant amplitude, but it'll just change like that through time. And we also learned about direct current, which will always be constant. Yeah. Another thing we learned about was resistance. It's how hard it is for the electrons to flow through the circuit. Resistors are basically objects that can be found in electrical appliances like light bulbs and refrigerators and computers. And these objects, they will increase the resistance and lower the current of the circuit. The unit is ohms, and it's represented with the omega sign like that. And this is how you display it when you draw a circuit. In the lab, we work with this special kind of resistors, which are little wires, and you can measure the amount of resistance each one has by this color-coded system. So basically each band represents a number, and you can know the amount of resistance each resistor has. The most important equation in electrical engineering is Ohm's law. It relates the voltage to the current and the resistance. So when you multiply the current, which is I, and resistance, which is R, you get the voltage. You can also just calculate the current of each component in a circuit, or you can add it all together and know how much current flows or how much resistance there is in overall. If you didn't understand much, this is a basic analogy to understand electrical circuits. You can compare it with hydraulics. So basically in a water current, you will start with a pump, which will start the water with a high pressure, and then the water flow can meet an orifice hole, which will basically increase the resistance and lower the water flow, and you have a low pressure. So when you go back to the electrical circuit, you'll start off with a battery and a high voltage, and the resistor will lower that current, and then you have a low voltage at the end of the circuit.
Now I will be talking about the hydroelectric project, and we experimented with a micro hydroelectric generator with our assistant Sarush and in the lab. And the generator is down here. So first the water flows through the intake and canal all the way down to the powerhouse where the generator is. And then the generator converts the flow of water into electrical power that can then be transported to the homes. The micro generator here is the one in the lab, and there are many parts to it. The variable frequency drive here, the current frequency and voltage meters here, the integral turbine, and the load elements back here. The variable frequency drive is basically a control measure for the rotation of the motor in the turbine, and the rotation of the turbine, it simulates water flow, in which case, so then you can convert it to electrical power. These are the meters in which you can monitor the output of the generator. And this is the turbine, which has a magnet and a loop of wire surrounding it, so that when the water flow goes through this loop of wire, it charges the magnet and converts it into electrical energy. These are the load switches, and they are used, well, when people use power in the daytime, it is a lot of power, and in the nighttime, most people turn off all of their appliances and resistors. So then the generator is spinning very quickly. So in order to control that rotation, we have loads. And what loads do is they slow down the turbine by exerting heat into, as we noticed, rods into a bucket of water. So that's basically a control measure for the generator.
Now we're going to talk about the solar panel portion of our project. So this is, I'm going to explain how solar panels work. So solar panels have two types of silicon. They have N-type and P-type. And to make the solar panel, you have to connect them together. And once you do that, when the sunlight hits the silicon, it creates a voltage difference between the positive and negative wires. And then if you connect a load or resistance on the end of those two wires, it will create an entire circuit for the electricity flow. So why solar panels? They have zero impact on the environment, so no CO2 emissions, reduces greenhouse gases, and helps help stop global warming. They are also very silent, or they are silent, unlike wind turbines or hydroelectric generators. They create no radiation like nuclear power, and also sunlight is everywhere where people are. So whenever you need electricity, you can just plug it in and the sun will be there unless it's at night. And then they are also very, very simple to install. So this is a experiment we did with two different types of solar panels. So we hooked up the solar panels to a resistance, and then in increments of like 500 and like 300 in increments, we lowered the resistance, and we looked at the voltage and the current, and we noticed that the voltage stays constant up until a point and then drops. And at this point is what we call the elbow of the characterizations. And at this elbow, you get what we call maximum power, because voltage times current equals power. And you want to find this point in all solar panels because this is where the solar panel is the most efficient. So you'll get the most power out of the sunlight you obtain. Also, there are 3 different lines for low intensity, medium intensity, and high intensity to explain how the power changes with how bright the sun is. So if it's a cloudy day, you'll have a lower intensity or like lower power than if it's a bright, clear day. Also, we looked at one solar panel was significantly older than the other one, and it just shows the improvement in technology and how this new one is significantly more efficient than the old one.
So after all these labs, we were able to decide upon our project for the Nicaraguan row house. We decided that solar panels would be the most efficient means to provide a self-sufficient electrical power for this home. Our prediction was to use solar panels to supply enough kilowatts to power all the electronic appliances in the home. And our goal is to make sure it's sustainable with these solar panels. So as you can see, we decided that 2 solar panels would be sufficient enough to power everything that would be in the house. For this example, we chose 4 LED lights, a television, and a household fan. So what do we know about Nicaragua? Well, Nicaragua has the lowest electricity generation in Central America. In 2001, about 47% of the country didn't have access to electricity. And also for reference, in this experiment, we'll be assuming that this area will have only clear skies So the solar panels will have the maximum amount of power output for the home. So for the wattage for each appliance, the house fan will have 100 watts. The TV will take up 70 watts. LED lights each will take 10 watts each, but there are 4, so that'll be 40 total. And then the stereo as like an extra appliance they might have for 60, having the total load estimation to 270 watts.
For this rural house, we chose the Canadian solar panel. Every solar panel has a data sheet that explains 2 different tests that you can make. The first test is the SAT, which is the standard test condition, which is basically the perfect conditions the solar panel can perform. In this solar panel, it should perform 255 watts. But since we don't live in a perfect world, we had to make other tests like the NOCT, the normal operating condition test. These tests are the real life outcomes the companies try to provide. In this solar panel, it would provide 145 watts. Since the total wattage for the house is 270, we need 2 solar panels that will be $544.17. The components for the installation are the solar panel, the inverter, and the system controller. The solar panel will transform the sunlight into DC current for the house. The inverter conditions the voltage to be fed into the appliances, and the system controller will monitor and display all the power or the electricity that is produced and being used at the house.
So in summary, we learned about the basic concepts of electrical engineering, which were voltage, current, and resistance, and we related them all in Ohm's law.
We also learned about the micro hydroelectric project and the generator that we worked with Sarush.
And we also learned about how solar panels work and why they're the next generation electricity.
With these 2 separate experiments, we were able to decide upon which would be the best self-efficient energy source for the rural home in Nicaragua.
Now we would like to give thanks to our advisors, Sarush and Dr. Singh, to our lead RAs and all the lead staff for giving us this great experience that could help us in the future to make the world a better place.
Thank you.
We would like to leave you with this quote: "Electricity is a modern necessity of life, not a luxury," by Franklin D. Roosevelt. Thank you.